Okay, so this will be our first lecture in the Enzymes and Energy chapter, where we're going to take a look at how energy moves through really any system, but we're going to focus, of course, on living systems. And from there, we'll go into enzymes and actually spend quite a bit of time talking about those because enzymes are absolutely critical to just about every process that occurs in a living cell. Enzymes are really, really important. So, with that, we are going to go ahead and talk about energy and kind of go back to some probably fairly basic, maybe grade school or even middle school definitions that you've probably all heard, 100 times. Energy is the ability to do work, and work is the ability to apply a force over a distance. Okay, so if you have energy, you can do work, and if you're doing work, you're applying a force over a distance. So, something else that you may remember, or probably do remember from grade school, middle school, high school, those kinds of things, is that energy comes in two states. There is kinetic energy, which is energy of motion. So a physically moving object has kinetic energy, but you can also think about kinetic energy in the form of heat or electromagnetic radiation, so UV light, infrared, visible light, microwaves, X-rays. Those all are types of kinetic energy as well. You could think about things that are radioactive giving off energy as well. Sound is a form of energy. So all those examples I just gave you are examples of kinetic energy, which is great, really important, but really our focus for a lot of these upcoming chapters is on potential energy. And so specifically the potential energy or stored energy, energy that's there but not currently being used in living organisms, is going to take the form of things like carbohydrates. So glucose has potential energy. ATP, which is a nucleotide, also has potential energy. And so those are really our focus, is converting one form of potential energy, for example, the glucose that you consume in a meal, into another form of potential energy, and then actually allowing that potential energy to become kinetic energy. All right, so as kind of like a more real world, easy to imagine example, we've got this girl here who's climbing to the top of a slide. So as she climbs, she's converting kinetic energy into potential energy. As she sits at the top of the slide, she has potential energy, and as she moves down the slide, she is again exhibiting kinetic energy. All right, so that's kind of our example of stored energy versus movement energy, those kinds of things. Again, the kinetic energy can take all kinds of forms. Mechanical energy is like the movement thing. Light, heat, sound, electricity, I didn't mention before, but also radioactivity are also forms of kinetic energy. So when we think about energy, one of the ways that we often talk about it is in the form of heat. And so heat is sort of a sense for energy transfer between two things. If you touch something that's hot, energy is being transferred from that object into your fingertip, for example. Or if you touch something that's cold, you are transferring your heat into that cold object, for example. So a physical calorie is the amount of energy that it takes, or the heat that it takes, to raise 1 gram of water by 1 degree Celsius. That's kind of a standard measurement of energy that we use all the time in sort of physical applications. Incidentally, when we think about calories in our food, like if you take a food label of your favorite snack or whatever, and the calories on there are actually kilocalories, so it's actually 1,000 of these calories to equal 1 food calorie. So it's actually a much bigger unit of measure when we think about calories in food as opposed to physical calories. So like I said, our big focus on this chapter, in the beginning of it, the first half of it more or less, is on chemical energy. And this is the energy that's going to power life. Right? So we're going to take our chemical energy in the form of glucose. We're going to convert that into a different form of chemical energy in the form of ATP. And then ATP can be used to do all kinds of kinetic sorts of applications inside of a cell. And that's really what we're focusing on in this chapter, but also the next two chapters when we deal with cellular respiration and also photosynthesis. So this is kind of like our lead-in chapter to the two more biochemical sorts of chapters coming up after this chapter. All right, so ultimately on Earth, probably 99% of all life on Earth relies on sunlight for energy, either directly if they're photosynthetic, or indirectly if there's something that consumes the photosynthetic organisms or consumes someone else who consumed a photosynthetic organism. So autotrophs use sunlight directly for the most part, and heterotrophs consume other organisms that have already converted that sunlight energy into bioenergy, so to speak. So sunlight's really, really important. Capturing that energy directly for the autotrophs is something that we rely on as heterotrophs because we can't use sunlight directly to fuel ourselves. You could go lay in the sun all day for 2 weeks or 3 weeks, and if you don't eat during that time, you're going to be really hungry because the sunlight's not going to do anything for you. So we have to consume either plants, which of course converted sunlight to carbs, or consume other animals which consume plants, for example. So lots of energy conversions here, right? So for example, energy conversion in the leaves of this peach tree, capturing sunlight, turning that into carbohydrates, which can then be channeled into the formation of these fruits, which you could then come along and take a bite of, eat one of these peaches, and it's got all kinds of good sugar in it that we can then use to fuel our own cells and our own bodies. So right there, we've got a couple of energy conversions right off the bat, sunlight to carbs, and then carb conversion from one form to another inside the body of the plant. So a lot of conversions here, and so we're going to be taking a look at the laws of thermodynamics, which describe what happens to energy when it's transferred from one source to another. Really, when we're dealing with chemical energy in living organisms, what we're really focusing on are the high energy electrons in those substances. So if we think about glucose that's made by a plant during photosynthesis, that glucose contains high energy electrons. And the reason why the electrons have a lot of energy is because the energy came from the sun. In the photosynthesis chapter, we're going to see exactly how that works. But the glucose that has this rich source of energy is that way because it was produced using sunlight, which of course is a massive, massive source of energy. Even all the autotrophs on Earth only use a tiny, tiny fraction of a percent of the amount of sunlight actually coming in on any given day. Most of it is not actually captured by living things. So it's a really, really immense amount of energy that the sun gives off. So we can think about these high energy electrons as having potential energy, almost like the little girl sitting at the top of the slide. And then as they give off the energy, as they go downhill, so to speak, as the girl goes down the slide, that energy is then used to do other activities, either used to make other forms of chemical energy or used to power different kinds of activities in a cell. So if a cell needs to move or build a protein or divide or detoxify something, all these things cost energy. And so the energy that they're using to do these activities is initially coming from things like glucose. Right, so the big lead-in energy molecule for all those activities is ATP. Right, there's all kinds of various energy sources in the world that contain lots of energy, but ATP is really the main one that cells use most of the time to do all these different kinds of activities that they need to keep themselves alive. A cell could be packed chock full of glucose, and if it didn't have a way to convert that glucose into ATP, it would starve, and it wouldn't have the ability to do all the different kinds of things that it would need to do. So everything must go through ATP before a cell can have the energy it needs to actually do stuff. So ATP has this structure. We've looked at this a few chapters ago. It's a high energy molecule, and so remember, things that are high energy tend to be relatively low stability. ATP has, adenosine triphosphate, has these 3 phosphate groups that all contain at least 1, and in this case 2, negative charges, which makes it a very unstable molecule. These negatively charged phosphate groups do not like being next to each other. They want to break off and go their separate ways, so it's a relatively unstable molecule. It's got a very, very short shelf life, so to speak. It doesn't really last very long. Cells really don't have a storage capacity for ATP because it's too unstable. It simply doesn't last very long, so you don't need to store it, can't store it. ADP, which is adenosine diphosphate, is kind of the same thing, but it only has 2 phosphate groups. ADP is kind of like a medium energy, medium stability molecule. And if we were to chop off the last 2 phosphate groups, we'd have AMP, adenosine monophosphate, which is a very low energy but high stability molecule, which is used for different kinds of things in a cell, but not really so much in terms of energy. It's used for more signaling kinds of things inside of a cell. So that's something we might talk about in a later chapter, probably in a different course even. So the next thing we're going to look at are the laws of thermodynamics. And again, this is something which you've almost certainly been exposed to before, but it's a very important concept, or very important concepts to have before we move forward and start talking about how cells actually convert different kinds of energy from one form to another. So thermodynamics is dealing with energy changes in the universe. All right, so the first and second laws of thermodynamics describe the availability and the usefulness or usability of the energy respectively. The first law is more availability or quantity. The second law is more usefulness or quality of energy. And we'll talk about both of those a bit more here in a second and really sort out the details of them. In biology, we sort of have this idea that biological organisms are based on the laws of chemistry, and chemistry is really just sort of a subdiscipline of physics. So just because we're dealing with living things in biology doesn't mean we can go against the laws of thermodynamics, for example, chemistry, physics, those sorts of things. We have to play with the same rules as the physicists and chemists deal with because, biology is built on physics and chemistry. So our first law of thermodynamics says that energy can neither be created nor destroyed. The amount of energy in the universe is a constant amount. It's a big amount, but it's constant. You can think about this as being the very first moment the universe sprang into existence. There was a certain amount of energy there, and that's the same amount that's there now, and the same amount that'll be there in a billion years. Right? The amount of energy in the universe does not change. So when I said the first law deals with quantity, what I really mean is that the quantity of energy in the universe is constant. There is, however, a caveat here. Even though the amount of energy in the universe is constant, the form that that energy takes is not constant. And really what I'm saying there is that you can convert energy from one form to another. That's okay, that's allowed, that's legal, we can do that, but we cannot change how much energy is in the universe. We can change the form that it comes in, but we can't change how much energy is actually there. Okay, so that's our first law, and that's kind of an important one that we're going to keep at the back of our minds as we go through this next chapter. Energy conversions happen all the time. They happen in our bodies. They happen in your car. The energy in the gas that you put in your car's gas tank is converted into kinetic energy in the form of your car moving down the road, but also lots and lots of heat, of course, as well. We've got a coal-fired power plant in this picture, kind of a schematic of what that would look like, very simplified version. But we've got chemical energy in coal being used to burn water. This heat, boil water. This heat is then used in the form of steam to spin a flywheel. And this flywheel, as it goes past these two magnets, generates electricity, which can then be used to do all kinds of other stuff, form of kinetic energy. So that's another example of an energy conversion. The amount of energy, though, here has to be exactly the same as the total amount of energy given off in each of these other steps. We're not creating new energy, we're just sort of changing the form that's there. The second law of thermodynamics is actually the more important of the two for our purposes. And the second law says that even though we can convert energy from one form to another, every time we do so, there's going to be a cost. All right, so I know it's different than the definition I have on the slide right now, but there's a cost to doing those energy conversions. Anytime you want to make something more complex in the universe, it's going to cost you energy. And anytime you want to break something that's complex down into simpler components, that's going to be a spontaneous reaction, meaning you don't really have to put that much energy into it. All right, so things that are building more complexity in the universe, those cost energy, and things that are breaking down in the universe are going to release energy, is a good way to think about it. And we'll talk about some more examples of that here in the next few slides, probably in the next section. Entropy is an idea of chaos and disorder, disorganization, randomness. Essentially what the second law says is that in the universe, entropy is always increasing. And really what that's relating to or pertaining to is the quality of the energy in the universe. So entropic energy is essentially heat. Heat is the most disorganized and least useful form of energy that we have available to us in the universe. But as time goes on, the longer the universe is in existence, the more energy that's there gets converted into heat, which again is an entropic form of energy, a very low quality form of energy. So if you were to carry this through kind of logically, what you'd kind of eventually arrive at is a conclusion that eventually the universe and all the energy within would essentially consist of heat. Right? If we could go all the way to the very last moment the universe is in existence, every last little bit of calorie in the universe would exist in the form of heat, which is really kind of a trippy thought if you think about it, but that's really what this is saying. Now, in shorter time scales, we're not really worrying about when the universe ends. We're dealing with, what's happening in our cells now. As our cells convert energy, say, from glucose to ATP, there is going to be some heat given off. All right, so the heat entropy in the universe is always increasing as time goes on. Every time we do an energy conversion, some of the energy, in fact, the majority of the energy is going to be given off as heat because that heat and the idea of entropy in the universe is always increasing. All right, so with every single energy conversion, some of the energy is going to be given off as heat. Now, this is another way to think about this. At first, it seems almost more like a riddle the way I have this worded, but it really sort of makes sense when you think about it. The general tendency of the universe is to take things that are more complex and therefore less stable and convert them into things that are simpler and therefore more stable. All right, so the idea of entropy, the universe is going from a more ordered state to a less ordered state, which means we're going from a less stable form to a more stable form over time. Okay, so this is a really good example of, I think, entropy in the universe. This is something that's very relatable. We've got a situation on the left here. We've got a very organized situation. And as time goes on, it tends to become disorganized. All right, now, you guys, I'm sure all know this. If any of you have kids, you know this as well. Wherever you have a living organism existing, chaos and disorder and randomness are going to increase. Like, you don't try to make your room look messy. It just sort of happens over the span of a few days or a week that, if you don't consciously pick up that room every day, it's going to start to get a little bit messy, right? So it's a relatively spontaneous sort of a situation in the sense that you're not actually trying to make it happen. On the other hand, if you want to go from disorganized back to organized, that takes effort. You have to consciously make the decision that, my room's a mess, I'm going to clean it up, let's make it look more like this. You got to invest some time and energy to make that happen. Going from left to right is spontaneous. You don't have to set your mind to it. You don't have to decide to do it. It just sort of happens spontaneously. Going right to left, though, does require some effort on your part and some investment of time and energy. So that's kind of the idea of entropy and randomness. The left to right arrow is always bigger than the right to left arrow. Anytime you're making something more complex and more organized, it costs energy. Anytime you're breaking something down, it's going to release energy. All right, so we're going to wrap up this section here. And when we start the next section, we're going to start looking at some more applications of energy and the laws of thermodynamics.